Je pense que tu peux renvoyer le lien sur... So, hello, can everyone hear me just fine? Like people in the back, people in the front? Okay? All right, cool. So, hello everyone. Welcome to GDSC Paris first workshop. This is the Introduction to Deep Learning workshop. And today we're going to be going over, we're going to start with a quick presentation that's going to last 30 minutes. After that, we're going to go off to a workshop that will last an hour and a half. So, a quick summary of what's going to be presented in this workshop. We're going to start, I'm just going to start with a brief introduction on who I am. We're going to see what is AI. We're going to try and define exactly what makes up AI. We're going to see deep learning in the real world, a few examples. And then after, we're going to see how it works from a little more scientific point of view, a technical point of view. We'll finish off with Q&A, and after the Q&A, we'll go on to the workshop, finally. So just a quick disclaimer regarding this entire workshop. It's not an advanced deep learning course. It's a workshop for people who have an interest in everything that's AI and deep learning related, but never really have the resources or really the know-how to start. So if you have any, prior knowledge to deep learning, I'm not sure you're going to learn anything new here, but it could always be helpful. So as such, there won't be any mathematics. It won't be too technical, but I'll try and go briefly over some important subjects that cover deep learning. So a quick presentation of who I am. Well, my name is Philippe Bouchet. I'm in the État Major Santé, which is the healthcare major. And basically, within this major, we specialize in everything that's AI, image processing for healthcare. And we try to apply these solutions to medical problems. So for example, this year we were tasked with creating a brain tumor detector. So an AI that's capable of looking at like MRI scans of volumes. And by looking at those volumes, it can say exactly where the tumor is located. We have another one that was dedicated to segmenting gray matter and white matter from MRI scans. And as such, we seek to bridge the gap between developers and doctors. So, enough about me. What is AI? Well, I'm going to try and answer that question, but first, it's going to be important to distinguish three main parts of AI. Because we say AI and it means a lot of things. So, as such, we're going to differentiate between AI, machine learning, and deep learning, and we'll see how they're all connected and why they have different terms for all these, all these concepts. So we're going to start off with artificial intelligence, and we can see that the definition here is mimicking the intelligence or behavioral patterns of humans or any other living entity. And I'm sure you guys can all think of one example, NPCs in video games, right? So you beat up an NPC, it starts running away, it starts defending himself. That's an AI. But the reason why it's an AI is just one line of code. It's just one if statement that basically says if I'm taking damage, I have to run away or attack the opponent. But this one if statement still counts as artificial intelligence because essentially what it's doing is mimicking human behavior. Even though it's just one if statement, it still counts as artificial intelligence. Now, that's a rather concrete example that we can all relate to, but there is a more abstract kind of AI. So we have these algorithms like minimax and A-star path searching algorithms, and they are very, they're AI, even though they're not like the classic AI that we know, but they seek to, as it said in the definition here, but they mimic human behavior. So just a quick reminder of these algorithms. So, A-star pathfinding, you have point A, you have point B, and you have to get there in the most natural way possible. It's mimicking human behavior. A minimax algorithm, a bit more complicated with this drawing, but it's just telling the computer, essentially in game theory, what the best move is. For example, when you're playing chess and you have a pawn, right? And let's say that your pawn is faced with a queen in its diagonal, enemy queen and an enemy pawn. Now, as a human being, it's really easy to understand which piece the pawn should take if it wants to put the enemy at a disadvantage. But a computer doesn't know that. So with a minimax algorithm, you can associate scores to certain pieces, and you can tell the computer that by taking the queen, you'll put your opponent at a greater disadvantage. So these are two algorithms I think are very well representing of AI, but it's still not the classic AI that we know. So we have to go one step further. And now we enter machine learning. Now, what is machine learning exactly? Well, the definition says right here that it's a technique by which a computer can learn from data, okay? And it says using data to improve a statistical model's accuracy. All right, so we want a statistical model to improve its accuracy using data. Now, what exactly does that mean? So if you guys don't have any idea of what anything's written here, it's fine. I'm gonna explain all this with an example called regression. Now, let's say you have a data set, right? You have X and you have Y. And in your X data set, you have 1, 2, 3, and they map these values into the Y column by giving 10, 20, 30. Now, this is, okay, it's a cool data set. It has three values, 1, 2, 3. But what happens when we add new data to this data set? Well, obviously, I think anyone can guess here that the value is going to be 40 because we can easily find this function that describes how new data will fit into the label data set, so the Y value, right? But it does get a bit more complicated when you add 200 samples, for example. So if we look at this, this graph here, we can see that we have 200 points from X that map to Y. But we can't have a simple function like f of X gives 10X, like we have here, to predict new values. So how can we estimate the value of new data when our data set looks like this? This is, it is a bit hard, but here we have 200 samples, we have features, we have one feature, and basically the feature is just the amount of dimensions that your function takes, right? So if you have a function f of x, it takes one feature. If you have f of x1, x2, so between the brackets, you have two features. So I chose features equals 1 because it's simpler. So we have to map a data set from x to y, and we have to find the function f that best fits the data. And you guys have all seen linear functions because, we just have f of x gives ax plus b. We have to find the a and the b that best describe the line that can go through this entire function, data set. Sorry. So how do we do that? Well, we use a concept called linear regression. And with linear, well, I'm not going to go into it mathematically, but once you use this concept of linear regression, you can find your A and you can find your B. And with that, it gives you this function that accurately predicts the trends of the data. So now you can add new X values. You can add new X values, and they'll give you Y values that basically fit this data trend, right? So if you add a new X that's, I don't know, -4, or that's a bit outside of this graph, it'll give you a value that matches this trend. So this is linear regression, and now we're getting somewhere in terms of a computer that can, AI, artificial intelligence, all this deep learning kind of stuff. So, but this is still machine learning. So now we have to go one step further, and this is where we go into deep learning. So the definition here is a technique to perform machine learning inspired by your brain's own network of neurons. Okay, and we call it deep learning because we use deep neural networks. Okay. Before I go into explanations for this, I'll just give a few examples just so that you can relate. But we have natural language processing. So as you guys all know, it's just giving, for example, human speech, human text to computers, and having those computers understand them, like what it means, like deeper. And then we have image segmentation, which is basically the same thing, but for images, right? So you give an image to a computer, it's trying to understand the semantics, the information that's contained within that image. So in order to answer the question, in order to define deep learning, we're going to have to define neural networks first. So what is a neural network? Well, I'm sure you guys are all familiar with this. This is a neural network. This is a very simple neural network. We have an input layer, a hidden layer, and an output layer. So in green, we have our input, which treats all the input. We have the hidden layer, which has all the hidden neurons that will transform the data from the inputs and pass it onto the output. And then we have our output layer, which basically gives us the result of what we are trying to predict, what we're trying to estimate. So in the case of linear regression, something like this could be very useful. So in order to describe how the data is transformed from one layer to another, what we have to do is we have to use weights and biases, right? So here we have X and we have Y. And basically what this does is describes how the data is transformed from one input layer to an output layer to a hidden layer, so on and so forth. And well, here it's a linear operation. We can see that we have X times W plus B, and it gives us Y, so it's a linear operation. But this is useful for simple tasks in machine learning, so something like classification, something like regression, but you can't go any deeper than that because we have a linear model. It's not too powerful. It's small, it's like 2 input layers, 2 input neurons, 5 hidden neurons, and 1 output neuron. Can't do much with this. So this brings forth some limitations. We only have linear activations. We only have 2 dimensions in this example. And by 2 dimensions, we have 2 inputs. So imagine we have an image of, let's say, 28 by 28 pixels, right? And they're images of handwritten digits. And we want to recognize the handwritten digits on these images. Well, what we're going to have to do is we're going to have 784 dimensions. We're going to pass all the value of the pixels into the network. But something like this is too small to even compute that, to even understand the abstract semantics that are hidden within that image. So what do we do? Well, since it's called deep learning, we're just going to add more layers. And here we can see that we just have much more hidden layers. And we're also using nonlinear models, nonlinear functions, sorry. But by adding more layers, what we can do is we're giving the computer more capacity to learn, right? Now, this was also very mathematical, but it's been technically proven. There's a link here if anyone's interested in reading the proof behind this. But it was proved that by adding more layers into your neural network, what you do is you give it more ability to learn. So, for example, if I take my example in which we have handwritten digits, right, and we put the handwritten digits inside the neural network, we can have each layer that's dedicated to understanding a different part of the image, right? So we can have one layer that's, for example, dedicated to finding the straight bar of a 1 or a 4 or 7. We can have another layer that's dedicated to detecting rounded tops, so like on a 9, an 8, or 6, so on and so forth. And then after we have a bunch of outputs. So this is a deep neural network. Now, I'm going to go on a few examples of deep neural networks. But before I go on, are there any questions for deep neural networks or anything relating to that? Okay. So I'm going to start off with a convolutional neural network. Now, it may look a bit complicated, but essentially it's rather simple, I would say. But what we do is we have this big network, and it's very specialized at treating images, so classifying images or even detecting objects in images. Now, what we do is that we take our image, right? We have our inputs, that's 28 by 20 by 1. And the reason why we have a by 1 at the end is because, well, if we had by 3, it'd be for the RGB channels, so red, green, blue. But here, it's only a grayscale image, so we only have one channel for the value of the pixel. So we have 28 by 20 by 1. Now, what we're going to do is we're going to take a convolution kernel. Now, a convolution kernel is just, I'm sure you guys have all seen matrices before. It's just a matrix, a square matrix, a 5 by 5 or n by n. You take it and you slide it across the entire image. And essentially, by sliding it across the entire image like this, what you're going to do is you're going to have this matrix that's going to activate certain features on the images, right? So you can have one matrix that's dedicated to, for example, detecting vertical lines, as we can see here. One that's dedicated to detecting horizontal, one, for example, right diagonals, right? So we can have these matrices, we slide them across the image, and what it's going to do is going to give us a feature map. And with our feature map, it looks like this. So here's our original image, and here's our example feature, well, our feature map for this image. So we take a bunch of different convolution kernels or convolution matrices, we pass them across the image, and it gives you all these different images that are, well, features that have been activated on the image. So for example, we can see that this one here in white, well, white values means that they have been that they have higher intensity. So we can see that here it picks up very well on this edge right here. Here we can see it picks up on this part of the shoe. Here we can see like it detects the sole very well. So by using these convolutions, what you can do is you can have this feature map, right? Now, once we have this feature map right here, at the second step, when we have N1 channels, we have 24 by 24 by N1. And our N1 basically represents the amount of images that we have. Now, this is great and all, but it's still very big. 24 by 24 is still a lot. So we want to reduce this. So in order to reduce this, we're going to perform a max pooling operation. Now, a max pool is just to reduce the size, you encode information, and preserve all the important parts of the images that say that this is a 2, for example. So you do a max pool and you divide the size of the image in 2. And here we get 12 by 12. So you repeat this process, so on and so forth, until you get to 4 by 4, for example. Small enough for the computer to understand, not big enough for us to understand. But the important part is that the computer can understand this. So once we have this 4 by 4 by N2, we're going to basically flatten it out. So take each individual pixel of our feature map and pass it onto our deep neural network, into our fully connected network. So it's just traditional neurons. It's going to perform some operations again. It's going to predict an output. So here in this situation, since we have 10 output neurons, the third output neuron would be activated, saying that it's a 2. And the reason, well, the mathematical function that we use to activate these neurons is a softmax function. So this basically says that the closer your, if the neuron tends towards infinity, you're going to have an answer that's closer to 1, meaning that that's what it detected. If your answer, if your neuron gives you something that's very negative, very close to minus infinity, you're going to have an output that's 0, basically saying, yeah, I'm sure this is not a 2, or I'm sure this is a 2. And using this function, you can have your network say, okay, I'm sure this is a 2, okay, I'm sure this is not a 2. And what we tend to want to do is kind of reduce the improbabilities, uncertainty, of the network. So when we have 0, 5, 0, 4, 0, 6, the network isn't really too sure on what it predicted. So just another for culture, I think I also wanted to present this network. I really like it a lot. It's called the Generative Adversarial Network. Now, the paper was published here. If you guys want to read it, it's right there. But basically, very simplified, what this network does is that imagine we have a generator and a discriminator, right? Now, these are in green. We see our deep neural networks. Now, what we want to do with them is with our generator, we're going to generate a bunch of fake images, right? And once we generate fake images from a bunch of noise, we're going to use our discriminator to compare the fake images and the real images. And by comparing the fake images and the real images, the discriminator is going to know, okay, this is a real image, this is a fake image, okay, and it's going to predict a score. With that score, we can put it down to the generator, pass it on to the generator to update the weights and biases that we saw before. And by updating the weights and biases, we're going to tell the generator, okay, you screwed up, but you can improve. You can make something that looks more like a real image. And now the generator, you repeat this process so on and so forth until you have a generator that's capable of generating real fake images. Now, once you have a generator that's capable of doing that, well, you have something like this. So this person does not exist. None of these people are real, but they were generated using this method, using generative adversarial networks. You just take a bunch of real faces, generate some noise, you compare, and after the network updates itself to get a score that basically fools the discriminator into thinking that he made a real face. So just a few examples of deep neural networks. Well, here's image segmentation. And this is basically having a computer understand the semantics of the image. So here we can see that it finds that it's a sky. Well, we have a sky in the image. It can find trees. And we see a little percentage right here next to what it detects. And that's basically the confidence with which it detects these things. So this is Facebook's Detectron, which is really powerful. But it can detect, for example, this person here at 100%, this one here at 99%. And it doesn't do so well with the people in the back here at 56%. But regardless, this is image segmentation, and it's a very powerful tool. It's very common in medical fields and self-driving cars, for example. And just another example of segmentation. Well, this is a brain tumor segmentation, and it was a project that we carried out this year. And basically, here are the results of our AI. So basically, on top is what our AI predicted, finding the tumors, and on the bottom is just reference, so that we can compare where those tumors were located within the brain. So these are just a few examples of segmentation. So this is great and all, but what are the frameworks that we use to develop deep neural network models? Well, we mainly use Python, and there are two great frameworks in Python. We have TensorFlow and PyTorch. So with TensorFlow, we have a rather simple API with Keras, and it's very easy to understand. It's what we're going to be using for this workshop. And then we have PyTorch. It is a bit more difficult to get into, but it does offer you a lot more control over what you write, over the code you write, how you interact with, for example, your hardware. And it is used a lot in research. So if there is anyone here who wants to go into AI research later on, PyTorch is something that you should learn. If not, you can use TensorFlow. It really gets the job done. It's not bad. And we also use C, C++, and Fortran. Now, I'm sure you guys are asking yourselves why we're using that, but the reason is kind of obvious, is because with deep neural networks, there are billions and billions of parameters that need to be calculated and updated and so on and so forth. It takes so much time. So doing this on CPUs is a bit difficult. So we use C and C++ with CUDA. And CUDA is basically a language that was developed by NVIDIA in order to allow developers to interact with the GPUs using C and C++ code or Fortran. And therefore, deep learning now in this day and age really depends a lot on GPUs. So why GPUs though? Well, if we want to understand why GPUs are being used a lot in deep learning, we're going to have to look at the hardware. So here's a GPU on the right, and here's a CPU on the left. Now we can just compare the components, and we can see that in the CPU, for example, we have 4 cores. Now these cores are ALUs, which are arithmetic logic units. And they're basically the cores that are responsible for performing operations like plus, times, subtract, etc. And we can see that we have 4, so that's great. But on the GPU, we can see that we have thousands, lots of cores. And because of this motivates us to write highly parallelizable code, which can accelerate your model training. So basically, in this day and age, if you want to do deep learning, anything related to deep learning, you're going to have to learn how to use a GPU. So this is why we use GPUs for deep learning. So just a few examples in daily life. Well, deep learning is used virtually everywhere. So for those of you who use Face ID on your phone, use it to unlock your phone with your Face ID. When you use Google Translate, that's natural language processing. Virtual assistants, that's also NLP. Now, colorization of black and white images. So you have a black and white image, and you colorize it using deep learning models and Snapchat filters. And the list goes on because deep learning is basically used everywhere in this day and age. So how does it work? Well, I promised I wouldn't go into mathematical aspects of this workshop. And well, I won't. But I'm going to go on a very basic overview on how it works from a mathematical point of view. So let's take our multi-layer perceptron, which is the name given to this network. We have an input layer, hidden layer, and output layer. Now, what we're going to do is we're going to feed our information forward on a first pass. We're going to take our data from our data set. We're going to feed it through the network. It's going to perform calculations, and we're going to have an output. Now, this output won't necessarily correspond with what we want with our expected output, right? We'll have a predicted output, and we'll have an expected output. So once we have these two outputs, our network can say to itself, all right, I think I screwed up here. I think I need to go back, update my parameters so I can have something that's closer to what we expected. So after this first pass is done, after this feed forward pass is done, what we're going to do is we're going to go back and we're going to back propagate throughout the entire network using, gradient descent, but that's another topic. But we're going to be going back through the network and we're going to be updating each weights and biases in the network in order to tell the network, if you want to predict something that's closer to our expected result, you're going to have to modify this, you're going to have to tweak this. And by doing this thousands of times, or 10 times, you get a network that's basically accurate enough to predict what you want. And this step is called gradient descent. Now, it's a very simplified explanation. There's a lot more mathematical components that go into this. But this is the general idea of how a network is trained. You feed forward your information, get an output, you go back, you correct, and you do this over and over again, and that's how the network learns. Now, I wrote here a gradient descent with normalized values. Now, I said I wasn't going to go into math once again, but I kind of lied. So we're just going to be looking at this drawing real quick. So what do we mean by normalized values? Well, let's say that here we have B and W, which are our parameters to our network, right? Here, let's say B ranges between 0 and 10, and W ranges between 0 and 20. Now, if we draw this function right here, we can see that it gives us this weird, like, surfboard stretched shape. And now, imagine if you drop a marble through this surfboard, right? It's not going to find the minimum right away. So, in order to have a shape that looks more like a circle, like a bowl, with a marble that can easily go down to the center, we normalize the values. So we put B and W between 0 and 1. So we change the range from 0, 10, and 0, 20 to 0, 1 for each of them. So we have this more uniform, symmetric representation on the right. Now, if we were to drop a marble, it would easily find the minimum. And the reason why we need to find the minimum is because by finding this minimum here, we can update the weights and biases of our network with the best parameters possible to have a predicted output that's closer to our expected output. Now, I'm not sure if that made sense, so if there are any questions with this. Okay. And so for this workshop, we're basically gonna be using Jupyter Notebooks. We're gonna be using TensorFlow 2.0, as I said before. We're gonna be using Google Colab for access to GPUs. So the task is going to be to create your own custom deep learning model to classify images. So that's the end of my presentation. If there are any questions, go ahead. You can ask. Yes? Well, the thing is, it's kind of done. Here, just go back. So, what do you mean by unordered way? You mean like we just look at this output neuron, then we update here first, and then we go and update here? Yeah. Yeah, I would say that it's ordered because with the way that okay, so the question was, is the way that the weights and biases of the network, are they ordered? So I would say that yes, they are, because the way that it is updated is using calculus, and it's called the chain rule. So with the chain rule, what you're going to do is you're going to find the derivative. Well, you're going to find the best way to change your previous parameters in order to get your expected output. But before that, you're going to also have to go back and find the derivative with respect to the derivative of, well, here. So here you're gonna have a first derivative. Here you're gonna have a second derivative, and so on. So it's kind of like a chain. That's why it's called the chain rule. So this is why this is why I can say that it is ordered. Are there any other questions? Okay, so there is a little formula here. I'm not sure. I don't know if you guys really had a lot of experience with deep learning, if you guys had any introductions to it before. So I don't know if this was either too advanced, not advanced. Yeah. Right. So yeah. Well, I didn't. It's not that I wanted to skip it. It's just I didn't really have enough time to. Okay, sorry. The question was, why did I skip activations? Well, the reason why I skipped it wasn't because I wanted to, but is because I thought I wouldn't really have enough time to go over all every single aspect of deep learning. But I was thinking to myself that maybe in a future workshop, one for example dedicated to convolutional neural networks, maybe I could go in more in depth with that sort of explanation. So yeah. So yeah, there's a little formula here. You guys can scan it. And normally so now we're just gonna take a quick 10-minute break. You guys can go out. You can just go smoke for a bit. And yeah, so we'll come back and we'll start doing the present TP. Thank you. Ok. Maintenant, les fichiers, ils sont. Je vais juste me mute. Okay, we're gonna continue. We're gonna be working on the notebook. So the break's over. So on Discord, there's a link to the GitHub where you can download the. We'll do a git clone the notebook, and once you have the notebook, you'll have it on your computer. And what you can do is you can go onto Google Colab. So you just search up. I'll do it right here. Just Google Colab like this. You go in here, click here, and you'll be presented with something like this. And what you're gonna do is you're just gonna go into File, Upload Notebook, and here you can browse your files. You can go into Downloads. I don't have it downloaded, but you can download it, and then after you can select your file. And once you're done with that, it will give you this. So once you guys all downloaded the files, once you guys all set it up, just let me know. Yeah. Okay, I will just. Okay. Is anyone having any trouble with? All good. Yeah, I can. Normally we send a mail with the link to the GitHub, and you could just do a git clone. You'll have the notebook. Did you receive the mail? Oh, seriously? Open? Oh. Okay, all right. So you guys can also just go on I don't have it. All Okay. So if you guys don't have access to it, you guys could always just go on File here, go in Open Notebook, go all the way to GitHub, and you can just type in GDSC-Epita. It'll give you this, and you can just select the file right here, Deep Learning Intro Epita. So normally, once you guys have all loaded it, you will be presented with something like this. You'll be presented with something like this, and what it is essentially, for those of you, I'm not sure, have you guys all seen Jupyter notebooks here? Who here does not know what a Jupyter notebook is? 1, 2, 3, 4. Okay, so basically what it is, it's an environment in Python that allows you to execute code in cells, right? So here, for example, I could just do this. I could add a new cell code. I could do something like this, print hello world. And the thing is, all the hardware isn't run on your computer locally. It's run from Google Cloud Services. And because of this, we can use GPUs because, as I said before, we're going to need GPUs to train the network. So here's it, print hello world. So all the explanations are given later on in the code, the notebook. And if you do want to have access to GPUs, you're going to have to go all the way here into Edit, Notebook Settings, and select GPU as your hardware accelerator. So you can save it. You'll have a limited number of hours per week, but should be fine for this this session. So someone asked how to use GPU. So all you have to do is go all the way up here onto Edit, go into Notebook Settings, and you can select a hardware accelerator GPU as your hardware accelerator, and you click on Save. Yeah. Well, you don't have to go on the GitHub page, but what you can do is you can go here. So on the screen, you can go into File, Open Notebook, you go all the way to GitHub, and what you can do is you can search up GDSC-Epita, press Enter, and you'll have this. You'll have two files. You have .github and this notebook. This is the one we want. It'll give you this. You click on it, and it's going to load, and it'll give you the notebook. So you guys managed to all load who hasn't loaded the notebook? Okay. All right, so if you guys have any questions whatsoever, you can just raise your hand and we'll try and answer. So we asked me a question, and the question was, what's the difference between these two functions? Well, the first function that we have here is just cross entropy. Now, it's a very basic function that basically you can use to measure the difference in information between two vectors. So here our vectors are y I and y I hat. But the thing is, when we have categorical cross entropy, it's very useful for when you want to do classification, right? So when you have multiple categories of things that you want to predict, use categorical cross entropy, because in general the way this formula is kind of described. So you have the first sum all the way on the outside, the one that goes from I0 to n, which is basically the same sum that you have in cross entropy. But then after you have another sum that basically iterates over every single class, right? I'm not. Does that make sense? Well, basically, check the difference between the two classes. Well, several classes. Sorry, I can't really hear you. Labels. Well, can you just speak a bit louder? In the first loss function, the labels are yi, and the predicted value is yi hat. So we have our prediction and we have our labels, and we kind of calculate like the difference between them. N'hésite vraiment pas à les répéter. Je crois que j'ai répété dans le. J'ai répété dans le. And by running these functions, what we can do is, well, it gives us a description of the dimensions of our data, right? So here we have 60,000 elements of 28 by 28. So we have images of 28 by 28, 60,000 times. And that's our training data set. So it's just a bunch of images. And so we have our Y train, which is just the labels. And we can see that we have 60,000, which is just the labels for each image in the X train data set. So if we just visualize our data, if we just select a random image from our X train, we get something that looks like this. And we can see that's just, well, the number 8 in this situation. I can run it again and it would give us a different number. And here we have a 2, for example. So if I print the labels, so we have all the possible Y values. We have 0 all the way to 9, and we have, well, our label for this image, 21,366, is a 2. So then after we go on to pre-processing, and I'll let you guys do that. If that was clear. The question was, where is the label for this image? What is the label? Well, the label here is just a value between 0 and 9 to indicate what. The label for this image is just a value between 0 and 9. So here we can see all the possible different labels that we can have associated to our images, right? They're just integers that contain one number, and the numbers are either 0 all the way to 9. And here we can see that our label for this image is 2. So the label is just telling the computer that this image, because the computer doesn't understand yet that this is a 2. So your label just says, okay, this image is associated to a 2. So, for example, we could have like values that are labeled as 3, and the image could be a 2, and the computer would see images of 2s as 3s. So it's just telling the computer what it is. There is a bug in the notebook, and the bug is make sure that when you arrive at this step, the fixed me for the normalization function, you're gonna have to implement a function. But what you can do by accident is that you can run this cell right here, this one, and if your function isn't defined, if you haven't defined it first, because it's still just a pass to not do anything, your value for x train is going to be overwritten. So if I run this, and after I do this, it's going to normally give me a bug there. So it says none type is not subscriptable. So you have to implement this function first before running this. And if you do encounter this bug, it's not a big deal. You just go all the way back up. It's a bit annoying, and you just load the data sets, and you should be fine. Just do the one hot encoding again, and then after you can go continue on to the normalization. So I hope that clears things up and avoids some bugs. So did you guys manage to do the normalization function? Is anyone stuck on the function so we can correct one? Okay. So the reason why I introduced NumPy before is because the thing is, if we want to normalize, right? So we'd have a value. I'll just open a new cell here, right? Imagine we have a value 125, and the max possible value for well, any value that can be had is 255, right? If we were to divide 255 by 255, it would give us, well, 1. And if we divide 0 by 255, well, it would give us 0. So that means if we divide anything in between 0 and 255 by 255, we'll get values that range between 0 and 1. Now, it is a bit tricky to do this in NumPy because I'm sure most of you would think that we could just do this with a loop, you know, for I in x, and then have to do something like xi divide equals by 255. But the thing is, with NumPy, you can apply operations to the entire array. So if we were to do this in NumPy style, what we could do is we could simply just do something like this. So x train, well, x norm would be equal to just x divided by 255. And this divides every single element, every single pixel of every 60,000 images just in one line like this. We run this. We got it. And after we can try it out like this. And okay. I'm gonna have to load the data set again. So once I do this, run the function again, It should be able to give us. Oh, okay. We have to load this again. So if I load the data set one more time and normalize the function, we can see that it gives us values between 0 and 1 for every single pixel in our X train array. Yes? I'm sorry, what do you mean? Yeah, you can use that formula, but since we're only dealing with 0 and 1, it's the formula is just simplified to dividing by 200. It's a simplification of that formula, so yes, we can use it. But for cases like where we have -1 and 1, we could use that formula. But for this situation, we're just going to stick to dividing by 255 because it gives us directly values between 0 and 1. So you just divide by the maximum. So I received a question, and the question is the scikit-learn library very bad? It's not very bad. It's just dedicated for a different field. So here we're using TensorFlow and PyTorch for everything that's related to deep learning, but scikit-learn is more dedicated to machine learning. So all this linear regression classification and so on. So they're two different it's not that it's bad. It's just that it's not adapted for this sort of situation. I hope that answers your question. I was muted. But the question was, why do we use softmax at the end instead of anything else like ReLU or sigmoid? Well, let's just take a look at the ReLU function and the softmax function, right? So if we look at ReLU, we see that it looks like this. It's a function that will give you 0 if all your inputs are negative, but it will give you the value of whatever you have of the neuron if it's above 0. So if you have a value of 7.5 in your neuron, it'll give you 7.5. But that's not what we want, because with our network, we want to have output neurons that can predict values between 0 and 1. So 0 for that's not what I'm sure this is not it, and 1 for I'm 100% sure this is it. And if we take a look at the softmax function, we can see that this is what it looks like, right? So with very negative values, we have 0 as an answer, and with very positive values, we have, well, 1 as an answer, but here for some reason they put it between 1 and 10, but the concept remains the same. So this is why we specify that at our last activation, at our last layer, we specify with the softmax function, so that can give us values between 0 and 1. If we were to specify with ReLU, then it would give us something a bit weirder. So for now, in general, we're just going to stick to the softmax function as our activation function for the output layer. So I hope that answered your question. So yeah, so we're going to define our model, and it's pretty simple. You can just do layers dot, and you can have like this option here to put like convolution or max pooling and so on, and you can give some different parameters. So 64 here is the number of filters. A 7 is the dimensions of your convolution kernel, and your convolution kernel is going to be 7 by 7. And in general, we're going to want this kernel to be an odd number, so 1, 3, 5, 7, and so on. And padding, well, it's not too important, but it just preserves the dimension of the image. Activation ReLU, and always for the first layer, we always have to specify the input shape. So here, since we have 28 by 28 by 1, we're going to have to tell the model that we have an image. We're going to be giving it images of 28 by 28 by 1. So now that we do this, we can just run the model, do this. Generates the model, that's done. We have our model, cool. But before we can even start training our model, what we have to do is we have to compile it. Now, compiling isn't like, well, in the traditional sense where we compile code, it's just specifying some, I would say, parameters for the model. So we saw gradient descent before. There are different algorithms for gradient descent and backpropagation. So we want to specify one algorithm, and it's called SGD, so stochastic gradient descent. And we're just going to be specifying it here. Our loss is going to be categorical cross entropy, because we saw all the way up here that categorical cross entropy is the loss function that's suited for this situation. So once we define our loss function, once we define our optimizer, we can also define metrics, so we can see what we want to keep a track of while the model is running. So while the model is being trained, you'll see how accurate it is at each epoch. So we're going to compile it. It's great, it's compiled. And now we can do a model.summary just to have a look at our model to see what it contains, right? So we're going to have a first convolution layer. It's going to take 28 by 28, and it's going to have 64 filters. So from the feature map, after our max pooling, we're going to have 14 by 14 by 64. So we're just going to divide the image in two and keep all the feature maps. Next, we do another convolution. So we'll have 14 by 14 by 32 divided in two again. And next, we're going to have 7. Now, a good rule of thumb is to stop doing your max pools when you have an odd number of dimensions, right? So here we have 7 by 7. If we divide it by 2 again, we'll get 3.5, but it's not too nice. So we're gonna stop here, and we're gonna flatten out our model. So we're gonna have 1,568 neurons that are gonna be connected to 128 neurons that will then again connect to 10 neurons out here. So this is just what the model looks like, and now we're gonna have to train the model. So before we train the model, we're obviously going to have to normalize the test and apply one hot encoding to the labels, to the test labels. So we're just going to do that. We're going to do this pre-processing on our test data set. And now we train the model by calling model.fit. We can call it with xtrain, ytrain, xtest, and ytest, the number of epochs, and our batch size. Now, unfortunately, I won't really have enough time to go in depth with all of this stuff, but you can look at the documentation at home, and you can run this, and you'll see that, okay, I just forgot to apply one hot encoding. Once we're done with that, once we can train our model, we'll see that we'll have 1 out of 10 epochs. So epochs are just essentially the number of passes that epochs are just the number of passes that you do to update your parameters. But for now, I am having a very hard time running this, so just give me 2 minutes. I'm gonna have to run this all over again. So if anyone's having bugs with the notebook, just let me know and I'll try and fix it. Okay. So now we can see our model is being trained, and we can see that it has accuracy. So loss, accuracy, val loss, and val accuracy. So accuracy is the accuracy that you get at the end of an epoch once your model is done training on the training data set. And val accuracy is the accuracy that you get when you use your network on the testing data set to see how accurate it is on new data, right? So we want to see how it performs on these 2 different data sets. So this is what accuracy and val accuracy are. Now, in general, you want to look at your val accuracy and you want to make sure that they're kind of on the same level. So here we see that they're on the same level. It's good. It's fine. It's even getting pretty accurate. And once it's done training, we can evaluate the model to see how accurate it is. So we call model.evaluate with our test data set. It'll give us the model results here. It's just loading a bit. Pas la question? Pas la question? So the question is, does the computing for the epoch and training, is it done with the GPU? So to answer this question, yes. We are using the GPU and we are training the network like this. If we were to use the CPU, it would be a lot slower. So yes, we are using the GPU. And how I came up with this architecture? Well, I can't really come up with it. It's just intuitively, sometimes when you do deep learning, you start to get a hang of things and feel for things. And you start understanding that if you do a convolution, then a max pooling, then another convolution and a max pooling, you'll start to understand that things kind of fit well. But this is just a standard architecture that really anyone can apply. It's not like a copyrighted architecture. It's just something very basic. So once we finish training our model, we can see that we can evaluate it. And we can see that it has an accuracy of 98.06 on new data. So given new images that it's never seen before, I can classify them with 98.06% of accuracy. So if we just take a look, if we predict the values, so we're going to store our y predict in this variable y predict, and we're going to just compare we're going to look at the image that we get right here. So we have a 3, and we have our expected value. So it's 3, and we have our predicted value. It's also 3. So we can see that our network performs pretty well on new data. And just I can run this again. And we can see that it's performing pretty well. It can detect all these new images. It can classify them correctly, which is what we want in general. So after this, now it's your turn. So what you're gonna have to do is basically the same thing, but just on a different data set, and it is gonna be a bit harder. So you're gonna have to. Well, I put a little bonus challenge where you're gonna have to try and get more than 75% on of accuracy of the test data set. If you can get that, well, then that's pretty good. But yeah, so you'll have a bunch of different fixed me's here. You can just fill them out, put the code that you need, and here I already load the data, and here I just give you some class names so you can know which class, which number corresponds to which class. So, are there any questions for the model here? For training, yes. Up. Oh, here. Stochastic gradient descent, yes. What do you mean? Every pass of an epoch or a step of an epoch? A step of an epoch? Well, yes, it would. So the question was, during stochastic gradient descent, what are we going to be looking at? Well, if that was, yeah. Right. So for what we're going to do is we're going to take like a bunch of batches of 128, and the thing is, there is also, well, the way it's trained is using mini batches, right? So one step will basically is have like the 128 images that you have, and you're going to be updating the parameters of your network by doing an average of an average of all the gradients that you get once you do the back propagation, right? So once you do back propagation on the entire network, you're going to be doing the average of the gradients. You're going to be using that to update your parameters. Yeah. Well, I think the way it's implemented differently is the way it's implemented in TensorFlow. I think it is a little different. I think they do say stochastic gradient descent, but I think that there is a bit of a mini batch approach by averaging all the gradients. Honestly, I'm not exactly sure how it works, so I can't really give you an accurate answer before I tell you something that's wrong. So yeah, I can't really answer your question. I'm sorry.
Après, on va vider la salle genre dans 5-10 minutes. Juste, tu peux dire, oui, il reste. Du coup,
Ah oui,
tu,
ok, ok.
tu vas me mettre.
Mute. Je suis déjà mute. Okay, so since the event is soon gonna be over, we're just gonna be wrapping up. So unfortunately, for those of you who weren't able to finish here, you can definitely finish at home. It's doable, and you can always send me a message on Discord on the GDSC channel. Just send me a message, and I'll try and answer my best. Now we're also gonna move on to the presentation of another event, which is gonna happen on the
next week on Monday at 6:30 p.m. So it will be an event on Docker. And very quickly, what Docker is: a solution to put your program or your application that you made in a specialized containers. You never have to say again this famous phrase, but it worked on my machine, but not on yours. So it will help you program better and run your programs in our application. And for more information, you can scan this QR code. It has a link to the GDSC page. So I hope I will see all of you next week, guys.
All right. So, are there any more questions for the deep learning workshop? For the model for yes? How would we use a validation data set? Okay. Well, the thing is, in TensorFlow, we're using it right here by specifying that it's the X test and the Y test, right? So we essentially have like a 80% that's 80% of our entire data set that's dedicated for training, and 20% that's dedicated for testing. Now we don't want to split this into test, validation, and train, because the thing is with TensorFlow, if you use the test data as validation data, it won't at all influence the updating of the parameters. So your network won't be biased towards your testing data set. So that's why you can use val accuracy. So once you train your network as a reliable metric. So if I just change the batch size here again, and I run this, we'll see that at the end we'll get a number that's validation accuracy, right? So we have accuracy and validation accuracy. They're both different things. Validation accuracy is the accuracy that you get at the end of the epoch, testing on the test data set, and the accuracy is just on the train data sets. In a way, yes. Yes, but it doesn't influence the parameters of the network. And PyTorch, I assume, I haven't really used PyTorch that much, but I assume it is different, but the implementation remains the same. Yes? Can you speak a bit louder, please? Save our network? To be honest, that is something that I never do. So I just go on TensorFlow on Google. I search up TensorFlow and how to save the network. And I think there is because what you need to do is you need to save the biases and the weights of your network, which is basically the most important parts of the network, which predicts your values. But yeah, I don't know. But you can always just like refer to the documentation, and we'll just give you a quick explanation on how to do it. It shouldn't be too difficult. Non, la question c'est comment sauvegarder le modèle.
Ah ouais, parce que je me suis déconnecté.
So, are there any other questions?
On va devoir vraiment vider là. Du coup, tu peux couper le stream, dis aux gens.
Okay. Oh, yes, one question? One question? Okay, so basically what overfitting is you have your network that's only trained on your training data set, right? So the thing is, you can have a network that performs perfectly on the training data set, but doesn't really generalize well on new data, right? So basically, what it would look like in this situation is if you had an accuracy of 90%, but your val accuracy was 50%. That means you're overfitting by a margin of 40%. Your network can't generalize well on new data. And this is what overfitting means. It can't understand new data. Does that answer your question? Yes, exactly. All right.
Faut vraiment qu'on arrête là.
All right.
On va se faire gentil ça.
Well, thank you very much. Thank you very much also for everyone on stream. I hope you guys learned something today. If you guys, as usual, have any questions, just send me a message on the Discord. I'll try and answer. Thank you.